You can recognize them at first glance. One magnet has a shiny silver surface. The other is dark and matte. The shiny one is neodymium. The black one is ferrite. But appearance is far from the only difference between these two types. So today we're going to look at what else sets these magnets apart. The main difference? The force you need to pull a magnet off a thick steel plate. We'll be comparing two magnets of the same size. Diameter 25 millimeters, height 5 millimeters, magnetized along the axis from bottom to top. Which one is stronger? It's generally expected that a neodymium magnet will be roughly 10 times stronger than a ferrite one. Let's verify that. We'll use a simple measuring device with a crank. Turning it lifts a suspended weight, gradually increasing the force acting on the magnet. The ferrite magnet managed about 1 kilogram before it pulled away from the plate. The neodymium reached around 8.3 kilograms. What about price? Neodymium magnets are more expensive, and the price gap typically widens with magnet size. For small sizes, neodymium might be just 3 times more expensive than ferrite. But for larger magnets, it can easily be 10 times the price. Ferrite is a cheaper material that gets pressed into molds, so its production is most cost-effective in larger runs. The tooling cost is spread across more units. Neodymium doesn't need a mold, but it uses expensive raw materials, and the manufacturing process is more demanding. So the bigger the magnet, the bigger the price gap between ferrite and neodymium. Of course, we're talking about eShop prices. If you had a magnet custom-made, a whole range of factors would factor into the final cost. But price isn't everything. Ferrite also has other advantages. For example, a much higher heat resistance. Neodymium starts losing its magnetic properties around 80 degrees Celsius, while ferrite can handle up to 250. In our test, we heated both magnets in an oven to 125 degrees for 30 minutes. After cooling, the neodymium's pull force dropped to 7.7 kilograms, roughly a 7% decrease. The ferrite stayed practically the same, within measurement tolerance. When we repeated the heating, this time to 225 degrees for half an hour, the neodymium's force dropped to 3.6 kilograms, a 56% decline. Ferrite held its original value even after this heating. In terms of mechanical toughness, ferrite is slightly more resilient than neodymium, even though both are brittle materials. In this test, a hammer will drop from roughly the same height onto each magnet. Ferrite survives the full range of impacts, while neodymium shatters at the very first level. This is what the magnets look like inside. On the neodymium, you can clearly see that the silver color is just a surface coating. But why does the magnet have it? It's a protective layer. Without it, neodymium would start corroding quickly. The surface finish gives neodymium not just a different look, but more importantly, different properties. Zinc is the most affordable option for dry environments. It's less resistant to scratching. The most common coating is nickel, a hard, shiny surface suitable for indoor use. It handles long-term moisture less well, though. Epoxy creates a continuous barrier against moisture and chemicals, but it's softer and can be scratched. Rubber protects against impacts and increases friction, but greater thickness reduces holding force. Plastic encapsulation seals the magnet hermetically, making it suitable for permanent submersion in water. Teflon is used in chemically aggressive environments. It's very durable but expensive and slippery. Gold or silver is mainly used where conductivity or appearance matters, not mechanical protection. And special coatings like perylene create a very thin and precise protective layer for industrial and medical applications. These are just selected properties. For more information, it's worth visiting the article on surface treatments. You'll find the link in the description. The last factor we'll cover is resistance to demagnetization. Ferrite magnets can partially lose their strength if they're exposed to a strong magnetic field. For example, when a neodymium magnet is placed against them, after exposing the ferrite to a stronger field in an unfavorable orientation. It's clear that its pull force has dropped below the original 1 kilogram. Neodymium magnets are much more resistant to remagnetization, so store ferrites at a safe distance from neodymium, ideally at least a few centimeters, and even more for very strong neodymium magnets. To sum up, the main advantage of neodymium magnets is high strength in a small size. Their downsides are lower heat resistance and lower mechanical toughness. However, there are also special variants that are corrosion and heat resistant, or come with a protective casing capable of handling demanding uses like magnet fishing. Ferrite magnets are weaker than same-size neodymium ones, but they're cheaper, naturally resistant to corrosion and heat without any special treatment, and can take rougher handling. They're the right choice wherever you need a reliable, affordable magnet, which is why they're a staple in offices, classrooms, and hobbyist workshops, and you'll also find them inside speakers.